Quasi-Z-Source Extended Boost Inverter with Active Z-Network Switch. Extended Boost Inverter with an Active Z-Network Switch is discussed in this paper. The suggested topology of the inverter, in comparison with Enhanced-Boost Quasi-Z-Source Inverters, EB-QZSI, which have two switched impedance networks, achieves the same boost factor with one extra switching device along with a reduction of 2 LC pairs and 1 diode. Besides, the current stress around switches is halved, which results in a larger reduction in switch conduction loss. Due to a reduction in losses, the efficiency of the proposed inverter is improved. Also, the proposed inverter maintains a common ground between the inverter bridge and the source. Besides, the input current is continuous for the proposed inverter. The operation principles of the suggested topology are described below. Some points of differences and similarities in the EB-QZSI and the suggested inverter topology are also described in the paper. The simulation results of the suggested topology are achieved. All the results are checked using theoretical analysis. Index terms: impedance network, Quasi-Z-Source inverter, active switched. Introduction in fuel cell and solar systems which are renewable energy systems. The Z-Source inverter, ZSI, seems to be a very successful topology as discussed in 1. ZSI contains unique qualities, which are not obtainable from a conventional current source or voltage source converter. To reduce the conceptual and theoretical problems which are present in conventional current source, CSI, and voltage source converter, VSI, 2, a Z-Source converter is used. The Z-Source converter eliminates the logical and technical obstacles and drawbacks of the conventional current source converter and voltage source converter. For any power conversion, the Z-Source can be applied. Turning on of the switches in the same leg simultaneously is possible in the Z-Source inverter that too. Without dead time. This is not allowed in conventional VSI and CSI. ZSI also has the buck boost capability with improved reliability of the converter. Given the above benefits, the ZSI also suffers from certain disadvantages such as a discontinuous input current due to the input diode in between input power supply and DC connection, failure to share a common ground in between them. To solve these issues, a class of Quasi-Z-Source Inverter, QZSI, is invented for joint earthing and continuous current characteristics with reduced ratings of components and source tension, but no improvement in boost factor is achieved when compared to the original ZSIs. To achieve a high boost factor, extended boost topologies have emerged. The proposed inverter in 4 is able to improve voltage boostability with switched inductor, SL, cells used in place of 2 inductors in the impedance network. However, the drawbacks are input current is discontinuous and still, there is no common ground between DC link and power supply. To reduce the passive elements of the impedance network, a switched boost inverter, SBI, is invented. SBI adding only one extra active switch to reduce the passive components. The boost factor of the SBI is the same as ZSI. By reducing the passive components, significant reduction in volume, weight, and converter cost is achieved in 5 and 6. To improve boost inversion ability, high voltage gain switched Z-Source inverter, HVGS-CSI, in 7 is invented. This topology brings together SBI and QZSI. But the problem with sharing common ground persists. By using cascaded networks, voltage gain can be improved. Extended boost ZSIs in 8 have 4 families. With the addition of LC pairs and diodes to the QZSI, other families can be realized to improve boostability. Besides, voltage stress across the capacitors is reduced in comparison to the conventional ZSI. The boost factor of Enhanced-Boost Z-Source Inverter with switched Z impedance, EB-ZSI, in 9 is very high and its expression is given in 1, where stands for boost factor and the shoot-through duty cycle is represented by. The proposed topology also suffers from certain drawbacks such as different ground points between DC supply and inverter bridge and the input current is discontinuous. To overcome these drawbacks, a new topology, Enhanced-Boost Quasi-Z-Source Inverter, EB-QZSI, is proposed in 10. The proposed inverter provides continuous input current by using 2 switched impedance network. The proposed inverter escapes the above-mentioned disadvantages in 9 and maintains a high boost factor. Fig 1 shows EB-QZSI with continuous input current configuration. To get a high boost factor, both 9 and 10 use 4 inductors and 4 capacitors due to which it becomes bulkier and heavier leading to an increase in converter cost. A new Quasi-Z-Source Extended Boost Inverter with an active Z-network switch is introduced in this paper. Proposed topology overcomes the above-mentioned disadvantages of a traditional ZSI. The proposed inverter reduces 2 inductors, 2 capacitors, and 1 diode, and adding only 1 extra switch as compared with EB-QZSI. The boost factor of both the topologies is the same. The proposed topology has all the advantages that are present in EB-QZSI such as, the input current is continuous, double ground features, etc. Also, the current stress around switches is halved, resulting in a large reduction in switch conductive loss and an improvement in overall inverter efficiency. The principles of operation are evaluated in Section 2. The EB-QZSI and suggested topology are compared with each other in Section 3. The theoretical testing of the proposed inverter is performed in Section 4 with simulation results. 2. Proposed topology. Fig 2 displays the suggested topology structure. Consists of 2 inductors, 1, 2. 2 capacitors, 1, 2. 4 diodes, 1, 2, 3, 4. And 1 active switch. Couples the source voltage to the DC link. A low-pass filter connects the DC link to the load. Remember that in this paper evaluation is done using a single-phase bridge inverter, but the suggested topology can also be extended to 3-phase circuits. A. Operation principles. For study purpose, there are 2 operative conditions of the proposed inverter, that is shoot-through state and non-shoot-through state. Operation principles of traditional ZSI and proposed inverter are similar. Fig 3. A and B displays the proposed inverter's corresponding circuits for the duration of the shoot-through and non-shoot-through conditions, accordingly. 1. Shoot-through state. When all the switches in any leg are switched on simultaneously, the inverter bridge is short-circuited, as shown in Figure 3a. This condition is called as a shoot-through state. A. Diode 4 and switch S is switched on, and the diodes 1, 2, and 3 are biased in reverse via capacitors. Inductors are charged in the shoot-through state. A. 2. Inductor voltages, 1, 2, and 2 capacitor currents, 1. 2, are derived in this state. Power is not transferred to the load, because the inverter bridge is a short circuit in this state. 2. Non-shoot-through state. Non-shoot-through state conditions are shown in Fig 3b. In this state the switch S and diode 4 are turned off and diodes 1, 2, and 3 are switched on. The source charges the capacitors via inductors. During this state, power is transferred to the load, which is stored in the inductors. Inverter bridge is open-circuited. In this state, the voltage and current relationship can be written as. In this paper, switches are controlled using control signals generated using the PWM control technique. Voltage gain of the single-phase DC-AC converter is obtained by where stands for the modulation index is the boost factor and the peak output voltage is represented by 0. Boost factor is dependent upon the PWM control technique. From 18, when the boost factor is high, automatically voltage gain is high. Simple boost control, SBC, in 6 is used in the proposed inverter. As shown in Figure 4, in one switching cycle, 2 shoot-through states occur. By using the SBC, current stress around the switches is halved as compared with the control method in 5. In a shoot-through state, a 2-phase leg is switched on simultaneously under the SBC, although the only one-phase leg is switched on in control technique. 5. By controlling the modulation index, we can control the duty ratio in SBC as follows. Fig 4 shows the PWM control technique for the proposed inverter. 6. 2 modulating waveforms, i.e. and are related with a high-frequency triangular waveform, i.e. to produce pulses. This pulse is used to operate the switches 1, 2, 3, and 4, compared to another triangle waveform, dashed line, with a double frequency and half of the amplitude of that of a constant voltage is produced for the 0 switch. The 0, a control signal, is then passed through the OR logic gate to produce the shoot-through states in the inverter bridge into the control signals of switches 1 to 4, D, inductors, and capacitors. Design. During shot-through state, the inductor currents rise linearly according to the above activity concepts. Therefore, the current ripple of inductors can be obtained in terms of 2, 14, and 15, as follows. 3. Comparison of proposed topology with EB-QZSI. The proposed topology is compared with the Enhanced-Boost Quasi-Z-Source Inverter for continuous input current configuration, EB-QZSI, which have 2 switched impedance networks. 10. Detailed comparison of the topology characteristics as shown in Table I. Detailed comparison of the topology characteristics as shown in Table. When comparing the topology characteristics, LC output filter and switches of the inverter bridge are not taken into account. It can be found from the table that the boost factor of the proposed topology and EB-QZSI is the same. However, the proposed inverter reduces 2 inductors, 2 capacitors, and 1 diode as compared to EB-QZSI. To reduce these passive components, proposed topology adding just 1 switch into the circuit. Input current ripple in both the topologies is approximate 0. Advantages of the EB-QZSI is no startup inrush current, common ground between source and inverter bridge. Input current ripple is approximate 0, and input current is continuous. These are all advantages also present in the proposed inverter by using less passive components. B. Voltage and current stresses. By using the same boost factor and input voltage, the proposed inverter compares voltage stresses across diodes, capacitor voltages, and switch stresses with EB-QZSI as shown in Table. In proposed topology, the voltage stresses across the capacitors 1 and 2 is higher than the EB-QZSI. But the entire voltage stress across the capacitors in both the topologies are identical. Because the proposed inverter uses only 2 capacitors and the EB-QZSI used 4 capacitors. As shown in Table, the voltage stress around the switches is the same in both the topologies. The total voltage stress across the diodes is identical in both the topologies as shown in Table. For comparison purposes, the same input voltage, voltage gain, and load are taken in proposed and EB-QZSI as shown in the table. The control technique of both the inverters is different. Because of this, the stress across the switches is not the same. In the proposed topology, SBC control method 6 is used and in EB-QZSI control method 5 is used. By using the SBC control method 6, the current stress around the switches is reduced by half as compared to the control method 5. As shown in Table, inductor currents of both the topologies are equal under the same operating condition. It is envisaged that the current stress across the diodes is generally less than that of EB-QZSI. C. Inductance and capacitance. From Table, the voltage stress across the inductors of the proposed inverter is double as compared to EB-QZSI. Current stress across the inductors is the same in both topologies, as shown in Table. In other words, with the same operating conditions, the inductance of the suggested topology is double than EB-QZSI, and the capacitance of the proposed topology is the same as EB-QZSI as shown in Table. 4. Simulation results of the proposed inverter. Simulation results are given to validate the process and efficiency of the proposed topology. Table displays the circuit parameters used to simulate the proposed topology. The simulation results for the proposed topology are shown in Fig 5. The suggested topology has been simulated using MATLAB/Simulink on the open loop configuration. The control method 6 is used to simulate the proposed topology. 2. Boost the input voltage. D equals 0.2 and M equals 0.8 is taken. RMS output voltage across the load is roughly 101 V, and DC link voltage is approximately 178 V as shown in Figure 5, A. To provide a pure AC supply to the load, the LC filter is connected as shown in figure 2. The value of output filter, inductor, and capacitor are 4.6 mH and 10, respectively as shown in table. The voltage across capacitor, VC1 and VC2 are approximately 180 and 108 V respectively, as shown in figure 5a. These results are matched with theoretical values, 14 and 15, respectively. The values of both the inductor currents 1 and 2 are increases in shoot-through state linearly, as shown in figure 5b. In non-shoot-through condition, inductor current decreases linearly. Accordingly, the above operational criteria in section are well confirmed. Over the analysis of the following simulation. The conclusion. In this paper, a new Quasi-Z-Source extended boost inverter with active Z-network switch is presented. The proposed inverter is compared with EB-QZSI. There are some advantages of the proposed inverter over the EB-QZSI such as 1. Current stress across the inverter bridge switches is less and it helps to improve the efficiency of the overall inverter. 2. Reducing the weight, volume, and cost of the proposed topology by reducing the 2 inductors, 2 capacitors, and 1 diode, but the boost factor is the same in both the topologies. 3. The power losses of the suggested topology are reduced by reducing the passive components that help to improve boostability.